a KRK Rokit 10.3 powered loudspeaker, or the back panel of it. The complaint was that the fuse was blowing all the time and obviously no power. So here is the power supply, and I'll go through what I've done with it. I've traced out the circuit. Now what it is, there's a 5-volt supply which runs all the time, and then there's the power supply which actually runs the amplifier, and that is only operating when a signal comes into the amplifier, so it's normally in standby. Problem was, of course, blowing switching FET. I mean, it's a typical fault, and here's the original out of it. So that was straightforward enough to replace that. Now normally when a power supply fails, the IC that drives the MOSFET dies with it because it's very closely connected. Now this is where we had some trouble. No markings on it. Obviously they don't really want you repairing this stuff. So the question was, what was it? All I could find on it was some kind of date code, and when I put that into the internet, it actually did come up with this IC NCP 1251, and when I looked at the data, it certainly looked like it was the IC, the same number of pins, the pin designations do the same thing, so it looked like that's probably what it was. So the parts were ordered, installed, and we can see, if I can focus down on it, the IC is there, just there, microscopic little thing. And that's what they look like in the packet. You can see the size of the pin next to it. So no power up despite replacing both of those, and this was all very curious because, you know, nothing had blown up. The driver IC gets its voltage from pin 5. Now in the data that's meant to be 18 volts. Now how this works, on this 5-volt supply which runs all the time, there is also another rail which is about 14 volts. Now that powers the switch mode IC for the 5-volt supply, and it also supplies through this PNP switching transistor the supply to the NCP 1251. And this PNP transistor is switched on by the optocoupler, and this is the standby switching, so the LED part of the optocoupler basically switches on when an audio signal comes into the amplifier. Alright, so 14 volts here, audio signal comes in, that switches on the transistor, and so we have 14 volts. No output, and I thought, well, is there something strange about this IC? So I made this little test setup. You can just see here, microscopic IC, just so I could find out what the IC actually needed to run, and sure enough, yeah, the supply voltage had to be 18 volts or it wouldn't start up. But once having started it, it could go down to, you know, about 12 volts or something, and it was happy. So that was some peculiar characteristic. So the next thing is, you know, what to do about it. Now my assumption is that the IC which I have used to replace it is not exactly what the original was, but we will never know what that was. So challenge is, how do we get it to work? So putting an external 18 volt power supply into here, and it did start up, and we had our 40 volts and our minus 21 volts. So all this part could be made to work, so it was a question of how we're going to modify this. Now this IC here, now this is another strange IC, absolutely no data on it. It's a CL21050H. And now it does turn up on the internet, but absolutely no data. But looking through some other search results, it did actually say it was equivalent to these two, and they do have data. But in any case, I traced out the circuit to see how this whole thing was working. I mean, obviously KRK aren't going to give me a circuit. Like most modern companies, they tend to be rather obstructive and don't want you servicing it. They want you to send it back and pay them a fortune. But anyway, I thought, well, is there a way we can make this power supply give out 18 volts instead of 14? But looking at it, the answer is no, because increasing the voltage here from 14 to 18 also makes the 5 volts increase, which obviously we don't want to do. So the other option was to get 18 volts from the rectified mains, or 340 volt supply, through a resistor and a Zener diode to clamp it. So 18 volt Zener diode will limit the voltage under no load conditions to 18 volts, which is what we want. And this filter capacitor here has enough charge to actually get the circuit started, and once it starts, this will drop back down to 14 volts. So to get the 18 volts, we use a 470k resistor from the 340 volt supply, so a little bit less than 1 milliamp, but that's all it needs. So far so good, and I'll just demonstrate it. I'll just plug in my isolating transformer. Okay, so what I've got here is an isolated 240 volt supply from a transformer. It goes through my series lamp panel, just to limit the current in case something bad happens. So when we short circuit this connection to simulate it coming out of standby, we should get some volts, and we do. That's our 40 volt supply. So far so good. I'll just disconnect that so it doesn't blow up. So these are the extra parts I've added. There's the 470k, and there's 18 volt Zener. Now this is the IC here that makes the 5 volt and the 14 volt supply rail. So having sort of proved the concept, yeah, the next thing to do is to tidy all that up. Yeah, put the 470k a bit closer to the PC board and the Zener diode. Then I can put it back in its back panel here and see that it works. This is actually a Class D amplifier, which is to be expected these days of power saving and political correctness and all of that. It's also got this fancy LCD display. Yeah, these are rather expensive, but anyway, hopefully it'll all function when I put it back together. I did actually take a close-up picture of what caused the problem. On the left you can see a partly carbonised insect which had got between the pins of the MOSFET, so 340 volts flowing from the drain through the insect into the gate of the MOSFET. Needless to say, yeah, the MOSFET would turn hard on and yeah, self-destruct. But yeah, the insect on the right is another one I found on the board, which presumably is what it looks like before it gets carbonised. Yeah, so high voltages and insects, yeah, they can blow things up. Okay, back to this power supply. I've had to re-engineer it again. Problem I discovered was, once it was back in the amplifier, when you applied the mains power, the 40 volt supply did not start up, and it turns out that my previous experiment, if you like, of connecting the 18 volt supply to the 340 through a 470k resistor would only allow this to start if the 5 volt supply had started up first. But when you turn the thing on at the mains, both supplies are meant to start at the same time. So I discovered that the 18 volt supply here needs to be 15 milliamps in order for the NCP 1251 to start up, and obviously the 470k resistor was not going to provide that kind of current. So how to get it? I looked at increasing the number of turns on this winding here to increase the original 14 volts up to 18 volts, but there wasn't enough room on the core to add any extra turns. I could use a great big resistor from the 340 volts to the 18 volts. It turns out I'd need about 20,000 ohms and it would be dissipating about 5 watts. So I thought that was a little bit impractical, because I'd have to mount the resistor somewhere off the board because it would just get too hot. So my final modification was these 4 components. What I've done is actually create a voltage doubler using the 14 volt winding. So we've got the 2 UF4007 diodes and the 0.0022 capacitor. So offload, in theory, it would be giving out about 28 volts, which is pushing things a little bit fine for the IC up here. So we've got the 18 volt Xeno diode again to clamp it, and the choice of capacitor is such that the minimal loading is put on this transformer, just enough to get the 15 milliamps, and the reactance of the capacitor also limits the current which can be applied to the Xenodiode so as not to overload it. So yeah, it turns out that it works. It works reliably on startup, and just to show that it's still working, here's this lamp here is on the 5 volt supply, and this is the 40 volt lamp. So we'll short out the optocoupler again, and the 40 volt lamp lights, so it still works. Alright, one word of warning about this power supply is that the main 330 microfarad capacitor remains charged up to 340 volts even when the power supply is not in use. There is no bleed resistor across it, so if you're working on one of these, be aware of that, because it is a shock hazard, and I've had something go splat when I've shorted out the tracks accidentally. Luckily I didn't blow anything up. Okay, here's the other side of the power supply. You can see, I'll just put that down here. This is the transformer for the 5 volt supply, which is always on, and this is the transformer for the 40 volt supply, which only comes out of standby when the amplifier board tells it to. Main switching FET just down in there, that's the thing that had the insect bridged across 2 of its connections. Rectifier, 2 rectifiers for the 40 volt supply, usual mains input filtering there. Okay, so that's it. Yeah, I'll put it all back together and hope that's the last I see of it.